Hello, this is Dr. Wood with Citadel Civil Engineering. This is CIVL202 Statics, Learning Objective 3.4.2, looking at truss analysis. It's a very exciting topic. I look forward to talking with you about it. We'll point out that this is statics, which is going to be foundational to our future studies in engineering. And so we'll want to make sure we master these concepts today, because today is the best day to learn statics. When we think about truss analysis is going to really, there's not going to be a whole lot new that we're going to learn. Rather, instead, what we're going to be doing is taking the ideas of rigid body equilibrium and internal forces that we already know and look at a special type of structure called a truss. And so once we get our truss definition out of the way, we'll be just using ideas that we've already talked about to further explore and analyze these systems. So to start off with, we want to be able to define a truss. And so if we look at this slide here, we'll see that this is the pyramid at the Louvre. And I think from this, we can actually develop some of our definition of what a truss is. And so if we come over here, we'll notice that, I want to try and if I can't make this a little bit more even. Okay, we'll notice that the Louvre truss is made up of slender members. Many slender members. And that's part of what it means to be a truss, is to have these slender members. So rather than having one big beam, we're going to have a lot of little members that bring it all together. And so we see all these slender members. Now, we'll also make the observation that when we define a truss, we're going to say that they are pin connected at their ends. So each of those members ends in a pin connection to some other members. Now, this should immediately start you thinking about frames, which are also made up of pin-connected members. The difference with a frame, though, was that we said only two members could come together if we're going to be able to analyze a pin-connected frame. Well, this is going to be a new way of analyzing it so that we can break these things down. Now, there's a special caveat to this that lets trusses work. So we're not done with their definition yet, but they are pin-connected at their ends. And so, like, for example, we can zoom in on the truss itself. This is the underside of the Louvre pyramid, and you can see all those very slender members that are all connected there holding the glass in place. Now, we'll also notice in this shot that we can see some of those larger brackets that are at the end of the members that hold the glass. And so it turns out that not only are they pin connected at their ends, they're loaded only at the joints. So with a frame, we said they were pin connected, but we said we could put loads anywhere we wanted to. And with a truss, the loads are going to have to be applied only at the joints in order for this to work. And so we can look at some other trusses here. This would be for my construction engineering major. We can see these slender members that are connected at their ends for both two different types of cranes. So the center lift crane here, it has those trusses, and you might be able to see they've actually got gusset plates. And gusset plates we wouldn't think of as being a pin connection. They would resist moment. However, because those forces, all those member directions are concurrent, we can actually model it as though it were a pin with no moment. So that concurrent force thing goes on for us there. Turns out another thing we talk about when we analyze a truss is that we're going to typically, at least initially, neglect the self-weight. So the idea is that like if we're looking at these cranes aren't going to weigh a whole lot, especially not compared to the size loads that they're able to lift. And so a truss is going to end up being a light or have a very high strength to weight ratio. So it's able to be very strong compared to how much it weighs. And so, for example, I could talk about, like, I have a little truss here made up of 3D printed members. It's a pretty good size. And it turns out that I can load this in a very heavy way. And even though it doesn't weigh very much, and in fact, this is only a 1D truss, I can direct your attention down here to where I have the truss set up. You'll see that truss sitting on the chair. And it turns out that I can lean on this pretty good. And I'm significantly heavier than the truss. But when I lean on it like this, um, we discovered that the truss is able to resist that weight. So there's a very high strength to weight ratio going on there. So same thing here. It's one of the benefits. Now I will ask a question. We said it's pin connected at their ends, which makes it a frame, right? A frame. And if they're loaded only at their joints, what's true about each and every member in a truss like this? If you look at it and you think about it, if it's loaded only at its joints, then every single member is going to be a two-force member. And that's really the key to what makes a truss, is that it's a frame of two-force members. That's really what unlocks our whole analysis ability for us there. So we can talk about trusses like this for frames. We might call the louvre. We'll go back to it. The louvre would be a space truss, so it's three-dimensional, right? We can get a little bit more simple, and we can go to a planar truss, which is what we see on that right hand picture. So we can talk about space versus planar trusses, and that's going to be looking at 3D versus coplanar truss members. Now, obviously, on that crane, there's actually two planes, right? But when we think about coplanar, we're looking at all of those members being built into one truss that way. We could talk about, for my mechanical engineers, airframes used to be made out of trusses like this, so this would have gone underneath the skin. Now we've moved mostly, except for like in ultralights, most airplanes now use a composite body system, but this is a World War II airplane where they'd attach the skin. We've gotten better at modeling and predicting and designing how the skin of the airplane can actually be a structural member, but previously these would have been slender members, pin connected, right, with loads applied only at their joints. That's where they would have attached the skin to it. We can talk about like a helicopter, like the Korean War era MASH helicopters that have the open truss in the tail out to the back rotor. And so again, it's very lightweight compared to its strength. And so there's another example of a truss. This is one of my favorite bridges. So of course, trusses have hold a special place in the heart of civil engineers because they're bridges. This is one of my favorite. This is the Firth of Forth. It was built in the 1800s. It is in Scotland, and it is fantastically huge. So there's three spans there, or three center pylons you can see, and this overall bridge is, I think it's a little over 4 miles long. So these are gigantic spans. Just to give you an idea, those upright vertical columns that you can see here, if I adjust the picture a little bit, we should be able to see that a little better. These vertical columns through here, each one of those is roughly 12 feet in diameter. So they're gigantic. So no longer applicable to just neglect self-weight. That's probably going to be a big deal. And it's designed to carry rail. So that's about the right size for two trains to pass each other as it goes along this bridge. It's got a smaller truss. It would be almost like a reasonable sized truss supported between those two pylons. Now, when we look at this, here's a picture. Yeah, I can go here. Here's a picture of the early designers. So we're looking at a cross section of two of the trusses and them illustrating how this thing works. And so what we've got here is that this guy is actually floating, like there's no support underneath him. And instead what's happening is that we have compression in these two members and tension in these guys' arms to hold his weight up. And then these counterbalances make it so that these guys aren't having to use a bunch of muscle. They're just having to have grip strength. And it's also putting a fair amount of compression into their spines, but that's allowing him to be supported. So this is one of their illustrations of the proof of concept of how that Firth of Forth bridge would work. A little closer to home, this is the old Cooper River Bridge. From what I understand, it was absolutely terrifying, but it would be an example of a planar truss because we can see that there's kind of the two planes as they go along compared to the space truss that is the Firth of Forth because it gets wider toward the bottom, narrower to the top. narrow at each end and then wider around the center supports. So again, planar versus space trusses. We can also talk about a simple truss, and a simple truss is going to be a planar truss made up of primarily triangles. And this is where we really want to live, at least in this class. We'll wait till a later day, maybe a structural analysis to get into things more exciting. This is a planar truss of triangles. And if you've noticed throughout, in general, our trusses are going to have a lot of triangles. And that's because geometrically a triangle, if you've got those three links of that sides, there's no other configuration that that triangle could work in, as opposed to like parallelograms that can skew. A triangle won't skew, and so that's really why we use those simple trusses. And again, even looking at this truss, we could say that it has slender members, but it doesn't look like they're pin connected, right? It looks welded together. But we can still say, because those members are concurrent, all passing through common points, we can model as a pin. We're going to say that the loads only go to the joints, and we can neglect self-weight. And so when we talk about the loads going to the joints, we can talk about our load path again. And so if I can point here for you, we'd have the rooftop, right? And we'd have tributary areas. So we'd have like the area that would go in this space, right? That would go out to this rail, purlin, and then we'd have kind of the middle that would go to the center purlin, and the one that would go up to the roof. And those purlins are going to split the weight probably about 50-50 out to the two edge planar, simple planar trusses, and it's going to load those trusses right at the joints. You'll notice here we got a pin connection over here, so two forces perpendicular to each other, and a roller, so just one vertical force here to hold the thing in place. And so when we've looked at our truss overall, we have talked about it being slender members, pin connected at their ends, loaded only at their joints. And at least in our initial analysis, we're going to say that we're going to neglect the self-weight. Now, the implication of this, as we've already talked about, is that we're going to have two force members. So the whole thing's going to be made up of two force members. And hopefully you remember. If not, here will be a nice little reminder that two force members can act in one of two ways. They can either be in tension or they can be in compression. And so if we think about this, we've got our tension forces there acting along the member like so, which means that if we were to look at, say, the joint over here, it would also be pulling along that direction. Or they could all be in compression, which means that it would be pushing on the joint coming off the member. So if you think of the joint as being that pin there. And so we're going to have tension or compression going through there, which means we're going to have no shear, don't have to worry about it, and no bending moment, don't have to worry about it. And that's a fantastic thing. And that also means that our forces, as we've talked about it, the forces will be concurrent at the joints. So the forces are going to be concurrent at the joint. So I'll blow this back up for us a little bit so that you can see what's going on there. So slender members, pin connected at their ends, loaded only at their joints. If we neglect the self-weight, it's going to be made entirely of two force members that will either be in tension or compression, and all the forces will be concurrent at the joints. So the joint force, because of this, our joint force is equal to our internal force. Which means that I can think about analyzing either the joint forces or the internal forces. The answer is going to be the same. Either it's in tension or compression. So that's what we've got going on there. Now, in order to do this analysis, we're going to use something called the method of joints. We've actually got two ways we could talk about this, but for now we want to do the method of joints. And the method of joints requires that we first, just like any internal force problem, we have to go find our external reactions. And so we'll solve for those external reactions by doing our free body diagram, our equations of equilibrium, and solving for the unknowns. But once we know everything external, what we're going to do is we're going to evaluate concurrent equilibrium, evaluate concurrent equilibrium at each joint. So we're going to evaluate concurrent equilibrium at each joint. So we're going to use what we call a joint window. To basically cut out an individual joint. Now, it's very important that we do not cut joints, because if we cut joints, we now expose all of those internal forces that we found when we pulled the pins, except that now, instead of having two perpendicular forces on each other member, we got a bunch of these concurrent forces all, and if you cut them, it just gets nasty. And so instead, you're going to look at the joint, not cutting the joint. And then for each one, you'll have to do your free body diagram. But the idea now is that we're either looking at a joint with forces on it, or maybe you could cut out the joint, something like that. So, for example, if I have this little truss here, we got this truss here, and then, we're in Charleston. People like to make movies in Charleston, or at least I'm in Charleston. So you can do your movie, so you can look through and you can decide, oh yeah, that'll look great. So you're going to do that where we might look at a joint. And so you build your little window, right? And now, hey, look, there's the joint I want to look at. And so it's going to generate, a little dot with some members on it, right? And when we do this free body diagram, whether we're drawing just a joint or a joint with all the little member sticks on it, either way, we're going to have all those forces going in. Now, when we cut a force and we expose two force member, only a normal force, we can say it's either in tension or compression. But what is our positive beam sign convention? It tells us that tension is considered positive. And so in each case, we will have forces pulling away from the joint. That's when we draw our free body diagram. Now, it may turn out that some of these are in compression, and so the math will work out to tell us that these are actually negative and they're in compression, but we're okay with that. We'll just make that interpretation at the end. And so we got a nice little song from the Lego movie. Y'all know this song. Everything's in tension. Everything's in tension. Two force members only work when they're part of a team. Everything is in tension for trusses, not beams. All right, so y'all love my song. I know you do. But we're going to assume at first that all the members are in tension, and then let the equations of equilibrium that we write from this free body diagram, either way, it's going to be the same free body diagram. Those equations of equilibrium will tell us whether they're positive or negative. Now, when we look at this, we'll notice that because it's a joint, we're looking at concurrent forces, we can only write two equations of equilibrium, some of the forces in the x and some of the forces in the y. So we're only going to get two equations, so we'll only be able to solve for two unknowns. So it's very possible we'll have to work our way through a truss in different processes. But as we do this, we'll be able to solve for our unknowns, and then we'll be able to repeat that process for each joint. So we'll repeat it for each joint. So that's trusses, and that's how we're going to analyze them using the method of joints. I should put a little of in there. Method of joints. I look forward to working on an example problem with you in class. I think it'll be a lot of fun for us. I really like it. It is a little bit on the time-intensive side, so just know that the homework problems will take a little longer because you're going to have to repeat for each joint and work your way through the truss. So if you think about that, if I were to look at a truss like this, this is the one we'll analyze in class, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8 free body diagrams, 8 equations of equilibrium, 2 equations per joint. So actually 16 equations of equilibrium, plus the fact I got to do my rigid body analysis to determine the external reactions for whatever loading I'm looking at. And so it's just going to take a lot of time for us to do it. So there's trusses in all of its glory. I look forward to working with you in class.